Okay, so we are going to look at radioactivity and in particular the rate of decay. Okay, so we have already said that in radioactive decay you have got a nucleus of an atom, and that this atom is unstable and it will break down, and when it breaks down it gives out some radiation which makes it radioactive. But we want to know how quickly, how much radiation per second, how quickly does it decay, the rate of decay. So we call something called the activity is the number of decays per second. Okay, so it's the number of radioactive decays per second. And we want to know how quickly that happens. So I want us to imagine that I've got here lots of dice, and each of these dice is one nucleus. So if I was to take one of these dice and roll it, if it is a 6, means it decays. So if I roll it and we've got a 4, this has not decayed. If I roll it again, I get a 3, it's not decayed. If I roll it again, I've got a 3 again, it's not decayed. If I keep rolling this, eventually I will get a 6. It's a 2, a 3, a 2. So the point about this is one of these atoms. One of these atoms, it is actually completely random. There we are, a 6. Okay, this has now decayed and it's given me some radiation, but I didn't know when. Okay, radioactivity is random. It is impossible to know when it will decay, and it is also spontaneous. It's random and it is spontaneous. Random means I don't know when it will decay, and spontaneous means I cannot make it decay. I cannot force this to be a 6. Okay, she's got a 6 again. All right. So we're looking at radioactivity is random. Okay, random means we do not know when a particular atom will decay. Okay, and the word spontaneous means we cannot make it decay. We cannot make it decay. Okay. Now the other thing I defined over here was activity. It is the number of decays per second. Number of decays per second. And I didn't mention, but it has a unit, the becquerel, BECQUEREL, or the BQ, becquerel, or the BQ. 1 BQ means 1 decay per second. Right. So that's our activity, the number of decays per second, and it has a unit of 1 becquerel. Now I have here lots of dice, lots and lots of dice. And the thing is, I don't know when each one will be a 6. But I do know that there are going to be some which are going to be a 6. 6, 6, a 6, a 6, oops, 6, a 6, a 6, a 6. So although I don't know when these will decay, I do know that there will be some which decay each time. These have now decayed. These have given out their radiation. They are no longer radioactive. But all of these remain radioactive. Oh, I missed a 6. There's a 6. These are still radioactive, so they will do it again. So I can put all of these back in my tub. Okay, and if I do it again, some more of them will be 6s. Ah, look, there's another 6, and another 6, and another 6. And each time I get some 6s. All of them decay. Some of them decay, but these ones don't. And again, these have now given out their radiation. Okay, and then I've just got these ones left. Okay. So this is the point of radioactive decay. We cannot predict when it will happen, but we do know that there is a chance that some of them will decay each second. It is actually measurable. So if I was to count how many are left and plot a graph of each time I throw the dice, this is a little bit like time, then we know if we're starting here, we know that after one throw, it will come down a 6th. This will be a 6th. And then in the next throw, there'll be another 6th. And the next throw, there'll be another 6th. And the next throw, there'll be another 6th. And the next throw, there'll be another 6th. So we actually, although it is random, although it is completely random, each time we know that we get a fraction each time. So if this is starting at n0, we come down to n0, 5/6 of that. Each time it comes down by the same fraction. Okay. So it's random and it's spontaneous, but we have this pattern. Now we want to look at something called the half-life. So this is where we started with. If we want to come down to where we have a half, so we want to come down to n0/2 and look at this. This is the time taken, the half-life, the time taken for half of the nuclei to decay. Now remember I said over here that it's from the nucleus. That's the nucleus of the atom. So the nuclei, that is more than one nucleus. So the half-life is the time taken for half of the nuclei to decay. Okay. So back over here. If this is our graph, this is the number of atoms or nuclei remaining, and then this is time, and the half-life is the time taken for half the nuclei to decay. And remember, this happens because it is completely random. Although it is random, we always get this pattern. We always get this shape. So, for example, there's something called carbon-14 has a half-life of 5,730 years. So after 5,730 years, if I'd got all of these carbon-14 nuclei, half of them would decay. And this half will remain radioactive. Carbon-14 has a half-life of 5,730 years. So after 5,730 years, half of the nuclei have decayed. How about if I go double this? If I was to go for 10,000, 5,000 is going to be 10,000.